Okay, so for the sake of time, I would like to start this meeting because we have a packed agenda. Thank you all very much joining this morning for the webinar on Powering the Future, Integrating Clean Hydrogen into the Power System. My name is Dolf Gielen. I'm the hydrogen lead in the World Bank, and I will be your moderator for this session. I'm very happy with this session because this is a topic which has been on the agenda of the Hydrogen for Development Partnership for some time, and it's very good that we get these inputs today. And also, this is a topic where we get increasingly questions in the World Bank from the client countries where we are working. So what I've seen in recent months is that the topic is high on the agenda, for example, in Brazil, Chile, Colombia, India, Mauritania, Namibia, and South Africa. So in most countries, once you start to talk about serious expansion of hydrogen, you run into the questions around the systems integration and especially power systems integration. And that include questions around is the electricity available? Is the sufficient grid capacity available? How should that be priced? Where do you place the electrolyzer in the system, close to renewable power or close to the ports? Do you transport electricity or do you transport hydrogen? How flexible are electrolyzers, or how inflexible are certain types of electrolyzers? So, and the list continues. And many of these topics will be touched upon in the presentations today. So we will hear 3 presentations from 4 presenters. You all have a lot of slides. I counted the total. I think we have 75 slides. So I ask you to be concise in your presentations. And without much ado, I would like to start with the first presentation. That will be by Dr. Cecilia Wollmark. Cecilia is the director of the Hydrogen Initiative Center, the Center for Hydrogen Energy Systems in Sweden, CHES, at Luleå University. And the center focuses on hydrogen use in industrial processes and energy systems in close collaboration with Swedish industry and global stakeholders. So, Cecilia, the floor is yours.
Thank you so much, Dolf. Can you hear me? Yes,
oh, thank you.
Great. And all the questions you mentioned are, of course, very, very familiar. So no wonder we have many slides. There are so many things to discuss here, but we will keep the time, of course. So I will see that I can start sharing a few of those slides here. Does it work?
We can see your slides.
Yes, great. So the first comment is that I personally have been working in the hydrogen area for many years. So that's with that background, I will also give you this presentation. You already mentioned the most of this, so I go directly into what we do in the center as a background. It's only one slide. We work a lot with education on hydrogen, which includes all different aspects of the hydrogen area. We have a lot of excellent demand-driven research. That's the way we like to do it. And as you said, Dolf, we really work in close collaboration with the industry and with international stakeholders. And we do a third thing, which we call accelerating hydrogen, which includes collaboration and communication. I will get back a little bit to give a few examples on the research in this speech. The background also very quick, because I'm very sure that all of you here are already very well aware of that we do see hydrogen as a component to to succeed with the greenhouse emission decrease that we have set forward that we would do and need to do ahead. And this has, of course, raised that we do need a lot of, especially green hydrogen, renewable hydrogen produced around the world. And there are different numbers and different forecasts for Sweden. This is one of the numbers given a few years ago by the Swedish Energy Agency, the 15 gigawatt electrolyzer capacity needed. But I will also show you a few numbers on what this increase means to us. We also have one of the world's largest electrolyzers being built in the north of Sweden today, which is about 700 megawatts, and we see several actually of those industrial sites in the construction at the moment. This is also a slide showing a little bit on all the activities which is already going on in Sweden. And for the background, we do have a lot of renewable power, hydropower, wind power, and so on in the country. A lot of biomass. We also have district heating, which is very interesting to see how we could combine with excess heat in hydrogen production or use. There are a lot of sites which have green carbon dioxide emissions. We have plenty of water, and there is capital available for investments. So what you can see in this slide is both on the left side here that we do have a lot of hydrogen refueling stations being financed, and there are 2 vehicle manufacturers, both Volvo and Scania. But not least, we have in these orange squares and the orange boxes all the industries which have put a lot of efforts into the hydrogen area and actually shown unique production of, which is most known, fossil-free steel already. And as we also represent the university, I like to mention that there have been already around 50 years of world-class research with connection to hydrogen, and of course also regarding the metallurgy questions. So that's also a little bit for the background. And this is really what I hope everyone of you here are already aware of, the hybrid plant, the first fossil-free steel production that actually showed that this is possible. We can produce steel based on hydrogen to remove the fossil fuels that were used earlier in this process. So this was built and proven and everything, and it started as late as 2016. So we see this as one of the very good examples of, if you like to do this, you can do it. And the second example that I like to give, that I also think the most of you already are aware of, is Stegra, which earlier was called H2 Green Steel, a very, very new company. It's only 4 years old, and they have already built so much of their green steel production plant that they are still planning to have the first production already next year. And these 2 sites are located in the north of Sweden, where we do need, of course, then a lot of more power. And there are further sites for ammonia production, and also further sites where the mining company LKAB have planned to have a few of these plants in near term. So in total, we will have seen, this is already a couple of years old, but this is some results from the research that we have done to understand how much would the increase of both electricity and hydrogen look like in like 25 years ahead. And here we could see that only in the northernmost part of Sweden, the 25% of the northernmost part of Sweden, we will have an increase of both electricity and hydrogen. Of course, hydrogen from zero gas use in this part of the area, it will be 3 to 6 times larger than today. So we have a huge demand of further production and distribution. And this is another way of showing it. This is from the consultancy firm Sweco, where I used to work. So that's a former colleague of me showing. And you can see all these red staples actually more or less corresponding new hydrogen production and then the electricity need for that. And then you should know that in the northernmost part of Sweden today, there are no headlines of electrical power, which then has to be built to manage these circumstances. So that's why then already here come to this very important picture showing to the right where new power lines are built now, and the Swedish TSO regarding power grids, which is called Svenska kraftnät here, they have already started to build these red main power lines to actually be able to support at least a part of the energy that these industries are expecting. But what we should know and bring with us here is that they have said and they have planned for or they are expecting there to be also hydrogen pipelines to actually supply this industry with this huge amount of energy that's needed. So in the picture to the left, you can see also the orange lines there showing the planned hydrogen pipelines that are supposed to be built. And the company that Nordion Energy that like to build these hydrogen pipelines have said as late as this autumn that they will try to complete to build 1,000 kilometers of hydrogen pipelines until 2030, so within 5 years, which of course are very huge plans, thinking about today there exists no gas grids at all in this part of Sweden. So this is what's to the right here are actually being built, and to the left we can see the orange lines, but you can also on this map, and you will have the QR code here to follow the map to see which are all the investments ongoing in Sweden at the moment regarding the hydrogen plants, industries, hydrogen refueling stations, and so on. You can also in this picture see a little bit about all the activities in Finland as well. So based on this, actually, this is in Swedish, but the title says it all. There is a new governmental task to the National Power Grid TSO to actually include the planning for hydrogen pipelines, and that was placed last year, and they are expected to present their first findings already this autumn. And this is then, I think it's so interesting to compare, since this is completely new. This type of co-planning hasn't been forced before. So based on that, I've collected some questions and both questions marks and some statements that I like to share already here. So I think it's so important to understand that the future needs, they are huge, but they are also unsure, which means that we have a lot of huge investments, which also, of course, will give a lot of local impact. We will see the impact of for example, the huge land use if we place wind power production additionally in this area, but the power lines and the pipelines, hydrogen pipelines, will also have some local impacts. But we also need to realize that there are differences between these two energy carriers. We can speak about that the whole day. We have to think about and include safety and security. We're also into the questions of the combination and cross sections, co-planning in the landscape of these two energy carriers. And we also have to consider whether local use or export is what we like to head for, and what different type of investments actually do mean for the future. And here we have one of the questions which we think about in Sweden, and that's the importance on which owner do we like to have for this infrastructure. Should it be the state or should it be investors? And we can see also in the near area of Sweden that we have different options, for example, even between Sweden and Finland today. So these are some of the questions and statements that I really like to share in this presentation. So from there, we can see in our all different research, we have research in 25 different subjects to cover everything from law to material questions. We have distributed and on research based, which are the main different barriers and drivers for this implementation. And these are some examples that we often like to share to actually break down to further and further different research projects. So this is also something we can speak a lot about, but I'd like to share you this one as examples and like a checklist to see if the main barriers really are addressed in the work in new projects. For us, that list of barriers has resulted in this map of research projects. Here we have the whole value chain from production, both production of electricity and hydrogen, distribution, storage and usage in all sectors. And we actually have all these 25 subjects I mentioned already involved in these research projects. So this is already a couple of years old, so we are adding new projects to this map all the time. But we see that there are so much research and development and innovation needed still to develop this area. So this is what we are very happy to do and to work with together with both industries and collaboration partners, as I said. And then I'd like to give you, since the subject of this specific seminar is the combination and the planning for the electricity grid, I'd like to mention a group of research which we do regarding the hosting capacity, how much hydrogen could actually be produced given the existing power grids. So we do research, and in this meeting I also have my colleague Peter Haig with me for further discussions in the end if that happens. So for example, we're working on operational risks. Could we decrease the requirements of the power grid to be able to produce more hydrogen? That's the question, and it's quite relevant question. How much could smart grid solutions help to increase the possible hydrogen production range? And of course, energy storage and flexibility solutions are both possibilities to increase the amount of hydrogen possible to produce with existing infrastructure, but we could also earn money on flexibility solutions. So this is very much ongoing research in our university. And here is an example and one paper where we show that if we can accept the curtailment only a couple of hours a year, we could actually increase the actual hydrogen production with 10%, as much as 10% of the peak load of the whole city. So these type of modeling and calculations is also part of our research. And then I conclude with some major points, and I also give you a recommendation if you like to hear more on me. There is a pod which is available for public, but here I have the 3 top of mind questions regarding need of both research, but of course also when we speak about implementation. I think it's so very important to support and to have that we could see the political decisions supporting this implementation. You're all very well aware about the risks and the different thinking and prioritization of the politicians, but not least that public stakeholders need to continue to support. This is something which is very, very important and which we also see very strong in the north of Sweden, that industry are working in very, very close collaboration with the municipalities, the region, us as a university and so on, which is completely necessary to get the whole value chain working. Next question is really how to keep the sustainable part of the development. We can see very, very difficult question regarding social acceptance, political acceptance, and so on. And here it's very, very much a question of supporting the attractive societies, I would say. And then my final takeaway is that what I miss personally when we look into the global plans of hydrogen distribution from one country to another, I really like to see the even longer term vision. What would it look like 75 years ahead, for example? I really need us to think about to decrease the amount of energy that needs to be shipped overseas, such that we can have the production as close to the need and the industries and people living there as possible. So that's what I would like to see, and would be very happy to collaborate further on also with any of you more interested in that question. So these are my top priority questions for anyone working in this area to have in mind. And I'm looking forward, of course, to the discussion here afterwards. So I give the word back to you, Dolph.
Yeah, thank you very much, Cecilia. It's very interesting to hear the case of Sweden, where so much is happening. And I'm sure there will be many questions, but I suggest we keep the questions till after the 3 presentations.
Yes, of course. I'm ready. Yes, of course. Yeah. Thank you.
Thank you very much. So with that, we move to the second presentation. We will have 2 presenters. We will hear from Alberto González Salas Mosquera, who is a partner for energy, resources and industrials at Deloitte, Spain, and leader of the global community of practice on regulation in power utilities and renewables. And his expertise is in electric systems, including the potential role of green hydrogen. And we'll also hear from Noé Augusto Alfonso Perez, who's a senior manager for energy resources and industrials, also Deloitte, Spain. And he's the coordinator for this global community, and he has a strong background in electricity grids and the integration of emerging electro-intensive industries, including green hydrogen. Gentlemen, the floor is yours.
Thank you very much, Dolph. Thanks for the opportunity of being with you and all the attendance of this meeting. With me is Noé, as you said, he's a part of my team. I'm partnering in Deloitte. I'm not going to repeat all the status that we have in Deloitte. But what we would like to review with you is our experience in the hydrogen, how the hydrogen needs to be developed around many countries that we are working with the World Bank and also the IDB and several multilateral entities, and also across Europe. Because I think the problems are more or less the same, not depending so much on the country. So I have a few slides talking about the importance of green hydrogen, but I'm not going to stop here because I think we all know why do we need hydrogen. I mean, we need hydrogen mainly because it's the only way that the world understands or know how to decarbonize certain industrial processes. Otherwise, we are not going to be able to decarbonize these things. And also because we can use it for another things and can substitute several fuel alternatives that right now we don't want it on the future. There are some uses of the hydrogen that we need to understand that right now they are not the best for hydrogen. Probably electrical solutions are much better than the ones than thinking on the hydrogen, but this will change. Once the price of hydrogen will go down, probably hydrogen will be the best option for this kind of decarbonization. But we need to understand also, I'm talking about the seminary that we have now, that hydrogen is not an energy. Hydrogen is a vector, an energy vector. So we need electricity to produce hydrogen, and we need electricity also sometimes for use the hydrogen. And this is a stress for the grids. This is the point of the seminary. As I was saying, we are going to use it for decarbonize the industrial processes. We are also going to use it for production of sustainable products. And an opportunity for the electricity system is that hydrogen will be the let me say, energy storage of the future. Much better probably than the batteries or a complementary uses for batteries talking in energy storage. But let me go through these. These are only data that are not so important, which is the challenge that we have for the grids. The challenge is to balance the growth of the electrification of the society that we have decided to do as a world. I mean, we have decided to decarbonize our economy through electrification and also with the uses of hydrogen that needs electricity. So we are going to increase the demand of energy, of electricity, on a huge amount for the world in any country, even though for production, hydrogen production, or even though for the regular demand that we are going to have as we are electrifying the economy. And in the middle, we have the grids. What happens here? When we are talking about hydrogen, we can think on producing hydrogen just with dedicated renewable generation, and we can also connect it to the grid. We can do both things. The issue is that once we have more than 4,000 hours of production of hydrogen, of electricity for production hydrogen, the price will go down. And the economics are quite relevant on this issue. So, except that the electrolyzers will develop on a different way, or there could be more flexible, as my colleague was saying previously, we need to think that the hydrogen production has to be connected to the grid, because this is the only way to put the price down. And if the price is not going down, we are not going to use hydrogen. So it's quite important to be able to produce hydrogen with renewables, dedicated renewables in the countries that we need it, and also to connect it to the grid, and also to let me say, increase the renewables on the grid. I mean, the country as a whole needs to develop renewables. So to be able to guarantee a project viability of hydrogen is directly arranged with the number of hours that it is going to produce the hydrogen. And
Alberto,
yeah, please.
can you back one
Yeah,
slide?
I go back.
Here, data, an important data, because what we see in the production and in the models is that when you have more than 44,000 hours of production, you can achieve a more stable cost in your cost production. That's illustrative, obviously, but we can see in the graphic in the right side with only a standalone solar plant. Maybe the hours are very limited to kind of affordable cost. And when you combine with different renewable technologies, you can achieve more hours, but only the most competitive plants probably will be that are connected to electric grid in order to ensure a stable supply with between the hours. Maybe it depends on the renewable resources connected to the grid in each system. How we will see in the next slide.
So when we're talking about producing hydrogen, we need to think that we also need renewables, not only for production for the hydrogen production, but also for the grid. Because if the electricity grid is not decarbonized, we are going to produce hydrogen, but it's not going to be green. So we need to be able to do both things on any country. Obviously, there will be countries, for example, our country in Spain, we have a big penetration of renewables, but there are several other countries that they don't have this right now, and they have to think about this. And that means to connect new generation on the grid for producing the hydrogen.
That point is very important because the opportunity of the hydrogen that the previous speaker said is to have green hydrogen or clean hydrogen in order to contribute to decarbonization, but the best opportunity is to reduce the dependence of the fossil fuels, especially in the countries where it's not available fossil resources.
So when we are talking about the grids, we need to be able to manage with the connection of the hydrogen to the grid, also to incorporate additional renewable production for the grid, and to maintain it as a renewable power system, because the grid is for everyone, not only for hydrogen production. And at the same time, and I think this is a quite important thing, hydrogen has to live with other decarbonization processes. I mean, for example, the transport and the electricity vehicles. So we need the grid to be able to support not only hydrogen, but also electric vehicles. Also, when we are talking about decarbonization through hydrogen for the industry, usually they are going to consume much more electricity, not only for the hydrogen, but also for the transformation of the processes. So the demand of the industry is going to be higher for the grid. Also, it's obviously, as we said, it's an opportunity as a battery energy storage, but also they are going to live with the new electro-intensive industries, like, for example, data centers or the mining bitcoins or whatever, that are also putting some stress on the grids in any country. There are many countries in the world, for sure you know this graphic, that need to decarbonize their electricity system much more than the other ones. It depends on the electricity generation that they have right now. It depends on which are the objectives of decarbonization that they are having. But when you are talking about producing hydrogen, you need to have a decarbonized system. Otherwise, you are going to produce it only with the dedicated renewables, and this is not going to be sustainable in the future. Let me say it like this. So countries like China, you were talking previously, Dolph, that we have projects in many places. Right now, I think it was this morning, one of the main companies in Spain has made an agreement with Morocco for developing the Sahara, huge production of hydrogen. Turkey, Egypt, Australia, all of them want to be in a position of producers of hydrogen. But their grids needs to support this on all the environmental that we have been talking previously. More demand of the industry, more demand for data centers, more demand for electric vehicles, etc., etc. And not all the networks are as ready as the other ones. I mean, and this is not only about developed countries or not developed countries. It depends on how is the power system developed through these years, is the history of the networks. It's how much are they ready for being able to support this pressure. Here you have a graphic about the frequency and the duration of the interruption that they have. You have on the quality of electricity, and as you can see, not all the countries are ready for this, even though they want to produce hydrogen or they want to participate on the decarbonization challenge. There are regions even in Europe. We have several examples in Europe where the congestion map are quite heavy right now, not thinking on producing hydrogen. This is, for example, Netherlands, or we have the same in Spain. We have several places. So when Dolph was talking on his introduction, where do we produce hydrogen? Not only which country, it's where in the country can we produce hydrogen. This is not so easy because the grid is going to be the point that is going to give you, if you are able to do this, if you are able to do it in 6 months, in 2 years, or in 7 years, because the grid needs to be developed.
Even you have capacity in the grids. it's important that because you have to connect the points of the production with the demand, and typically are not together. Most of the projects are focused in the hydrogen balance, but in the future project planification, you have to reinforce that networks because instead you need the connection to a grid. You need to make new investment.
Talking about this, the main projects I think across Europe for producing hydrogen are next to the consumption, because it's quite difficult to think about producing hydrogen very far from the consumption, as we don't have obviously the pipelines for using the hydrogen, but also because the network needs to be ready for this. And we have to think that when we connect a hydrogen plant to the grid, it's not the demand of the hydrogen plant the problem for the grid. The problem is that over that, you need to be able to maintain the system working for the rest of the users. So that's the problem for the grid. And even the investors can pay the connection to the grid. Of course, they are going to do it. The users, the rest of the users of the grid, are the ones who has to pay for the rest of the connection that you need to do. And this, let me say, fight with the regulatory environmental of each country. So it was very interesting what Cecilia said previously, that it was Norway. They have obliged the TSO to plan the grids taking into account the hydrogen. For example, a regulatory measure that can help the hydrogen to develop and to be able to mix not only the hydrogen development, but also what the grids needs and which is the needed for the rest of the system associated to the hydrogen. We need a very good planning of the power system, thinking on all these things, and also some regulatory mechanisms that permit to have the framework that gives enough flexibility to adapt the power system. We need to think that usually the companies that owns the grid in all the countries are regulatory companies, and they cannot invest if the regulatory environment doesn't let them to do it. So, we also we have some challenges, or let me say tactical challenges, like the procedures that you have to connect anything in any grid, usually much more in Europe than in other countries. But when you are blocking a point for, okay, I want to develop a hydrogen project, you are blocking the system. You are saying to the system, okay, we are going to put this demand here. Until we don't have the project, we have to develop all the grids. But you also compete with data centers, with industrials, with all the rest of electricity demands that we are going to have in the future. So which are the procedures that we have? Which is the regulatory limitation for the investment for the grid owners? And also, if there are incentives for these grids, it's going to be it's going to be a challenge and also an opportunity for the development of the hydrogen. The last slides are more or less the summary of what we've been talking about this. Which are the DSO and TSO opportunities, and what do they need usually in all the countries? They need to speed up the investments. Let me say that hydrogen and mostly data centers, and when we are talking about hydrogen, the decarbonization of the industrial processes is something that we didn't plan 10 years ago, and the grids are not planned for 1 year. The grids need to be planned for 3-5 years later. So all the plans of the grids need to be updated, and we need to speed up those investments. They need to be flexible for the expansion. We need to develop best grids that the ones that we have right now. Cecilia has said it. Smart grids, flexibility, the storage in the grid. This is not so easy to develop on the grids. This is not something that we can do in 1 year or 2 years. It needs to be planned, and the companies needs to have the right environmental, regulatory environmental to make those investments, because otherwise it's not going to be developed. And this is everything about the remuneration model and also the tariff. Who is going, we say in Spain, who is going to pay for a party? There are many things on the grid that are usually paid by the users. So the users needs to understand what are they paying, and the tariff needs to be right designed for paying only the things that the user is owner, not the rest of the decarbonization that we are going to do, because otherwise the tariff is going to be increased too much, and this is going to be a problem for any politician or any country. Let me go back. I don't have too much time. You are going to have the presentation for any discussion. Our conclusions about this is that we need to ensure the renewable grid access. I mean, to be able to connect all the renewable that we need, and also the demand that we are having, including the hydrogen production. We need to advance on a proactive and cross-sectorial approach to the grid planning. The example that Cecilia said is, for me, it's a great example. In many countries in Europe, all the companies are demanding this. Okay, we made a bet as a country for the hydrogen. This makes a lot of sense, but we are not making the same bet on the grids, and the grids need to be a part of this. We need to develop the remuneration models, not only for the owners of the grids, but also how do they get these incomes? How does the tariff has to be adapted for the new environmental that we are going to have? And we need to strengthen the system flexibility and stability, because otherwise hydrogen could be a problem in some places. And I don't know, but we will see the questions later. I think I've been on time. So I give you again the floor, Dolph. I'm ready for the questions later.
Yeah, thank you, Alberto and Noe. I think this was very, very interesting. It's more of an grid operator perspective, and I think that the next presentation is a nice continuation of that, because we'll hear from Antonio Illicito, who is an advisory board member of Dii Desert Energy, but who's also employed by Terna, the Italian transmission system operator, in international operations within strategy, planning, and dispatching. And his field of activities includes coupling of systems, including hydrogen and EV impacts on power grids. And he is active in many international organizations. Antonio, the floor is yours.
Thank you. I understand the slides will be moved centrally. So thank you. If you can put the first one, or shall I share the screen?
Ignacio, can you show the slides?
Yes, absolutely.
I can share the screen. Maybe it will be better. Can you see them?
Yes, Antonio.
Can you go to presentation mode? Yeah. Thank you.
Like this?
Yes, perfect.
Yes. Also, I present here some results from SIGRE, which is an international electrical engineers and grid professionals around the world. We have recently concluded a thorough study on hydrogen, which will also be mentioned later on. There I'm chairing the Committee for Power System Development and Economics. I understand the time here is paramount. So just to show a storyline here, I will touch upon that we need both electrons and molecules for decarbonization. And the main point of this very interesting webinar, because the first one I participate, which is exactly focusing on this integration between the two systems. I'm active both in the in the business environment where electrolyzers and hydrogen sector operators are trying to have their business case closed by some kind of incentive, and they are not concerned about the grid. And I am also in some grid circles where electrolyzers are seen as an extra new load coming. I think both these have to be merged with the win-win solutions. And then I will give an example, because we were also requested to give some concrete examples using hydrogen for bulk long distance transmission of energy from MENA region. Well, first of all, one of many possible representation why we need both molecules and electrons. And molecules here we are talking about hydrogen and derivatives, because there are some decarbonization processes which can be easily or cheaply done by electricity, others which cannot, and the same is conversely valid also for the gas, not gasificable end users, let's say. So there will be a mix, which is actually a technical economic minimum between how many electrons, how many molecules. This depends on the processes, but also from other drivers. Some of them are also country specific, so there is no one-fits-all solution here. So in general, taking a very system-wide approach, I will use this system approach all throughout my presentation. And from an energy system, not only electricity, gas, hydrogen, these three have to cooperate a lot. We can talk about direct or indirect electrification. Direct is when we can change an industrial or residential or building process from a fossil energy source to plain electricity. So this is direct electrification, and this is one of the most important drivers of electricity system, including grids in the next decades. And for the other economic sector, we talk about indirect electrification. If we are referring to green hydrogen produced with green electricity. So in the end, is electricity used for final users through also this hydrogen process. So always starting from abundance and more and more cheap availability of renewable sources. That's why until 10 years, 20 years ago, it was not feasible. Now we start having a lot of cheaper electricity from renewables, so we can use it also in this way, indirect electrification. For reason of time, we don't go all through this table, but just to mention the principle that which way direct or indirect electrification is better depends mainly on technologies which change over time. Luckily, we are evolving fast in the technologies, and on all the cost of the supply chain, because case by case the supply chain can be different. Not only production of hydrogen, but also delivered hydrogen cost is relevant here. All in all, we can say this starts to be a bit old already, because something is already being challenged in the transport sector. That for light-duty vehicles, there is quite a convergence or consensus, international consensus, that direct electrification with battery electric vehicle is more convenient. While for heavy duty and other forms of transport, this is still something to be observed. Depends on technology. And for industry, there are definitely some high temperature industrial processes which cannot be electrified directly, so the molecules are the best one. And then domestic commercial, it depends on each single case. So this is something which has to be taken, because it's not electrons against molecules, it's not a religious war. I want only electrification, direct or indirect. It has to be seen sector by sector. I would say even sometimes case by case. And this is because we have to incentivize new technologies. So we have to incentivize those which will be more efficient from decarbonization point of view. €1 spent and how much grams of CO2 avoided are there, but also efficiency in terms of energy and efficiency also in terms of infrastructure, because if we can use existing infrastructure, we save a lot of new investments. So there is no consensus on all the decarbonization best processes, but there is consensus that it will be in the end, the final case will be with a lot of electricity and also some decarbonized heat.
Oye, el otro día lo buscamos.
And the
Energy era, ¿no?
hydrogen will come from electricity. So we will have the three main vectors: heat, electricity, hydrogen. The yellow boxes that you see here means that together with this new future system, we need to develop and deploy a lot of storages in form of heat storage, battery storage, other kind of electricity storage, and then all the hydrogen transport and storage infrastructures. So it's not only the electrolyzers. In the end, one of the many nice figures you can find around in literature, in webinars, is that if you consider the integration of electricity networks with gas, then part of the gas becoming hydrogen, and some new hydrogen network being developed, also thermal network, district heating, and other kind of networks will be developed. All in all, electricity networks plays a central role, because when you talk about sector coupling, most of the times the sectors are coupled through or with electricity. So that's why I focus my presentation especially on the electricity side. So the impact on the power system, we can say, I say there are four main points. One is electrolyzers come with a lot of new renewable generation. So there is an issue of the need of a huge quantity of new generation capacity. The second point will be on the planning, the third on operation, and the fourth on flexibility. Let's see them one by one. First of all, as it was mentioned also in the introduction, the very first decision when you have a business case, because you don't build the electrolyzer and just operate it waiting somebody to offtake and buying electricity day by day. You need long-term planning. It's an industrial investment. So you need to know where to localize your electrolyzer, how to transport and to the final use. So the two main cases, but these are extreme, then a lot of partial in-between cases are possible, is to place either electrolyzer where the renewable are available, so you avoid transporting electricity, but then you have to transport hydrogen, or the opposite, to place electrolyzer where the hydrogen demand is, and then you need to transport the electricity until there. So there are many considerations which can be done here, but the main point is, first of all, for very short distances, we talk about hydrogen valleys, and this will probably be the first cases to be built, where both electricity production, generation of hydrogen and consumption of hydrogen, they are all concentrated in a small area, so no transport and storage infrastructures are involved. And so it's easier to close the business case. And for very long distances, power lines are not really feasible. We cannot go intercontinental with the power lines, especially if there are water seas between them. So, for example, also just crossing 1,000 or 2,000 kilometers of sea is already putting electric cables out of the comparison when transporting hydrogen. But the main point here, as you see in the bottom, is that as it is, I have to add something to what my colleagues in Deloitte were saying before. TSOs, the grid operators worldwide, are typically by regulation obliged by license, because most of them have a legal monopoly, are obliged to connect whoever makes a request, demand or generation. So typically, if I want to build a new factory or a new electrolyzer, I just make a connection request, and the grid operator is obliged to propose me a scheme. There can be some discussion about who pays what, which portion, but the point is, when we talk about gigawatt scale, many electrolyzers in Europe, some years ago, we were thinking the European Commission was talking about hundreds of gigawatt scale electrolyzers. You cannot consider this as a normal new load coming as a new factory or whatever. This becomes a strategical energy planning decision. It should be taken together with a lot of coordination in order to optimize the overall CAPEX, OPEX, energy efficiency, and infrastructure utilization. So it becomes very complex. It was very interesting for me to know about the Swedish example, where the electric TSO has been entrusted also to plan for the hydrogen, which is not the case in all of Europe yet. So these figures, you can see again the positioning of electrolyzers. We made a small taxonomy according to the location, respect to the grid, the physical location, the connection type, and also the operation. We will see now in the next slides a different operational mode. All of these are determining the impact on the grid and the integration challenges and possible solutions between hydrogen and electricity sectors. What is for sure, as you see in the title here, I will place that electrolyzers, but also the opposite, regenerating electricity with hydrogen, shall become not only new loads, but new components of an integrated energy system. We have to reason like this since the beginning. Otherwise, we go to inefficient solution, to bumpy transitions. You see the 4 cases here from left to right. Connection privileged to the H2 demand, because maybe you don't have a network, a pipeline to transport your hydrogen, so you have to do this. Or electrolyzer, which is standalone. It's both connected to an electricity grid and then a hydrogen grid. So this is most flexible possible operation from the electrolyzer point of view. Or a connection on the opposite side to power supply. And the last one is hydrogen bellies. It's almost a self-standing system. And let me go a bit faster here. The flexibility need has been already said by previous speakers. So now we will go from a principle of operation, a philosophy that generation has to follow a load, which is an external variable. We now have the opposite. Generation becomes an external variable because it's weather dependent, and we don't want to curtail, to lose the possible generation of electricity. So the load and the storage or interconnection exchange flows have to follow the generation. So for the grid operators, you understand this is a complete 180 degrees paradigm shift. It's not easy in all the technical aspects, but they are not part of this webinar. So we investigated in particular what kind of flexibility can arrive from electrolyzers in terms of grid services. Here you see some acronyms which may not be known to everybody, but mainly just let's say it is about frequency regulation and voltage regulation, also active power regulation. So with the 3 main technologies that we have now and in the foreseeable future, we see all in all, let's look at the final bottom sentence, that actually electrolyzers, which are not built to have a flexible operation, because they would like, as we have seen in a previous slide of other speakers, to run for as much as possible number of hours per year, and possibly at 100% rate, so they can have their capex and initial cost and all fixed cost spread on more hours, and so reducing the levelized cost of hydrogen. But actually, if we design them, if we specify them, and if we operate them in a certain way properly, they can easily provide these grid services. It's a low-hanging fruit. Just have to be designed like that. It is not in the business plan of who buys, who commissions an electrolyzer, but with a little effort, they can do also this, and of course get a revenue stream, because providing grid services means being paid for that. And this is about short-term flexibility, because we have to operate the grid in the range from milliseconds to seconds to hours. But then there is another aspect, which is not on the electricity side, is on the wider energy side, of which system, of which electricity is only a part. We need, for the reasons which have also already been explained, so I will not lose time on that, we need long-term flexibility. Just think that sun is shining only a central part of the day, so we need to cover the day-night cycle. And also, all in all, we have monthly or even seasonal cycles to cover. So we need very long-term flexibility. And if you see this graphic, the red part is about hydrogen. It's one of the few possibilities. It's technically possible today, and for some performance point of view is also one of the best places. So we need hydrogen also for this, and this cannot be given as a service to a single electrolyzer. You need a system, a regulation in place, and somebody has to pay for a sort of strategic reserve, as we have now for gas. In Europe, for example, we have obligatory 3 months gas stocks to cover not only the seasonality but also the possible shocks, supply shocks. So this should be translated for the hydrogen. And so I will just take a summary of here. We need hydrogen, we need its flexibility in short term, which is a sort of demand response, if we want. From electrolyzers operator. To do this, we also need not only technical possibility from electrolyzers, the willingness of the owner, because nobody can be obliged to provide flexibility, but also we need to decouple electricity from hydrogen. That is electricity input from hydrogen production and hydrogen production from hydrogen output. So we can only do this if we have a storage and transport, so let's say a logistics system. So to do this, we need to develop logistics, which cannot be done by individual electrolyzers, private investors. This has to be a system. So as we did for electricity and gas network, we will have to have an hydrogen logistics system, which has to be planned together with the development of electrolyzer, which have in their turn to be planned together with the new renewables. So this paramount coordination is, in my opinion, the most difficult part. And we risk the mismatch otherwise, because the transition period will be long and hopefully as a little bumpy, but it will be bumpy. What we see already now, for example, sorry for this is an extra example, in the automotive electrification industry, we went too slow, then too fast, and now some big companies are suffering because this is the bumpy transition type I am referring to. So electricity is needed for hydrogen, hydrogen is needed for electricity. This taxonomy that we have done now is not on the planning, but is on the operation. Once you have this electrolyzer, which can be flexible, we can have different type of operational mode. If you see here on the second column, starting from left, first of all, that was referring to European continent. We focus only on electrolysis based generation of hydrogen, only on grid, only domestic, because if it is not domestic, there will be imports from other countries. So this will not doesn't need any integration with the existing grid, electric grid. There will be some hydrogen produced not with electrolysis, for example, the so-called blue hydrogen. And of course, again, this has not any impact on the electricity grid. And we will have a portion which is questionable. I've seen also on the chart before that there are different opinions of electrolyzers which are placed off grid, that is with dedicated RES. Again, this is not impacting on the main grid. So if we focus only on the on-grid domestic electrolyzer based on the upper part, we eventually, I spare here all the reasoning behind, we identified these four operational mode, let's call them business model actually. The simplest ones are, one is demand driven. You just produce hydrogen as much as your off-taker asks you. If you don't have logistic system behind, this is the only way you can do. But the best, the more smart is market price driven. I use the electricity when it is low cost, and so I store hydrogen somewhere and I sell it when the price I decouple my production to my sale through some storage. And remember that also in another graphic we have seen there is a high dependency of production cost, not only from factor capacity, load hours, full load hours, but even more from the cost of electricity. Base load, many hydrogen consumers are base load, industrial loads. So that is something which try to maximize the capacity factor, but is not good grid friendly, because base load means no flexibility. The last one is a bit ideal. It's the one which consider in the business plan also selling of system services. Sorry to rush, but so we have seen that a crucial point, which is again here in the title, we cannot consider only electrolyzers as the physical interface between electricity and hydrogen sector. We have to consider all what is around. So all the infrastructure of hydrogen, which are very costly, the long time to be built, long time to recover the capital. And one shortcut is repurposing the pipeline from natural gas to hydrogen and repurposing the underground large storages for natural gas again to hydrogen. So this is saving a lot of money, but it's for safety, technical, operational speed, etc. requires still some adaptation. And also you cannot do it overnight, because the transition, again, the problem, the final situation in the year 2000X, there is a consensus, but how to reach there? It will be a bumpy transition. This is the point. Again, just to show the type of study, we have done the taxonomy of this operation configuration. You can call it also business model, according if you look as a electrolyzer private operator or a public grid operator, is that the provision of flexibility, but also the possibility, negative possibility to create a grid congestion, the risk of creating grid congestion, depends on this identified operational modes and on the presence of a logistics system. And so you have good cases and no good cases here. So don't let's forget that the green labeling is also very much influencing here. For example, in Europe, it has been imposed this three principle that first to label low or zero carbon and hydrogen produced, it must be produced with assets, new assets built on purpose, either if they are grid connected or not. This is not, I mean, there are sub cases, but the important thing is that you don't have to cannibalize renewable production, which can go to decarbonize other sectors. For hydrogen, only for hydrogen, there is this additionality principle. And then something which is related to the grid, the physical capacity to move electricity from one market zone to the other and from one time period to the other. These are the market zone and the time slot are the ones used in the electricity market. So if these two principles are not respected, you have the concrete risk that some of your hydrogen is produced with fossil fuels. So to be on the safe side, that was initially decided, although it is not straightforward to be applied always. But this influences all what we said before, the business model, the operational mode, and then the integration. So we have also this regulatory point. So here, I would like only you to look at the right part. So the point of view which I'm bringing here is from the grid operator. So we have to run the grid in short term. So we look at the short-term flexibility, but we have also to be a power system operator, not only the grid, the whole system, which means the grid and all the devices which are connected, the generation, the distribution, transmission, consumption, etc., and the sectors which will be coupled, EV charging in the future, heat pumps, electrolyzer, etc. So there we need the long-term flexibility. You see in the bottom, if you are interested to deepen the recent SIGRE technical brochure, which I was referring to. This is available on the e-library of SIGRE. And just a final point about using hydrogen as a vector of energy. Vector, it means it is always a vector, but a vector means to transport a long distance and bulk quantities, more quantities of energy that can typically be transported by electric lines. So that is an example of some calculation, which is still the figures are exemplary. You could adapt to any case, and they were calculated a couple of years ago. The prices, reference cost here are changing very rapidly. So just to go from a generic point in Middle East to another generic point in Europe, according to distance and other characteristics, the main thing we can say is that if the final use is electricity and the power line is overhead, which is much more cheap, typically this is the most convenient way. But if the final use is hydrogen, the costs become comparable, of course. So it's not only a cost of transport. You have to have a full end-to-end business case, a use case, I would say. And if instead of overhead line, we have to do cables, submarine cables, which are costly 7, 8 to 10 times more. And then again, the benchmark can go more to the comparison can be more favorable to hydrogen. So this is how you should, if you want to do this calculation, you should assess with all these parameters and boundary conditions. As the Desert Energy Advisory Board member, I would just before closing to mention that this is an important case worldwide, because there are a lot of possibility of cheap RES production, as you can see in the upper left side, in all the countries of that region. And indeed, in the bottom left, you see projects which are coming in the way. Some are also huge, like NEOM project in Saudi Arabia. In the end, this is again not completely recent, I think 1 or 2 years ago. If you sum up this and only this, these are only the ones which have been announced and have more concrete possibility of being built. They arrive to 10 megatons per annum, which is maybe by coincidence or maybe not the imported demand of hydrogen, which initially the European Commission had set for Europe. So this is a concrete case, and from the transportation point of view, you can use both the gas pipelines which are there, or shipping. If you are, for example, in Oman, in that area, it might be more worth to ship with the ships, which then can go everywhere in the world. The 3 main markets will be Europe, Far East, and North America, very probably. And just one mention to the upper left corner of this page. If you see the blue line is the European demand of electricity. Here we remain on electricity. The point is, even in the future, there will be enough capacity and space and for wind and solar to cover all the European demand, but at a much higher price. You see how much higher is the blue line respect to the other two, which means if you integrate the electricity systems, you can transport electricity to the overall benefit. So what we call normally in electricity cost benefit analysis, also towards regulators, the social welfare. And this is the very last, just mentioning that in DII there are many publications. Most, if not all of these, are publicly available on the websites and also free of charge, spanning all the aspects. You see one of the last ones is liquid hydrogen, because this is another possibility of transporting it. So not if we are ships, and in some of these also ammonia as a liquid transport is investigated, because it is technically much more feasible. So there are various ways to transport hydrogen. So if I have to just finish, I will not go through the takeaways, but just let's say that hydrogen is not only the production, not only electrolyzer, which is a physical interface with the electricity system. We have to look at the whole infrastructure and end-to-end system to find win-win solution between the business case and the needs of the system. Sorry if I went a bit long.
Thank you very much, Antonio. And I thank all the speakers for staying on time. We have 15 minutes left for the Q&A. I hope what you got from the 3 presentations is that there is indeed an important issue around systems integration, which is not an easy issue. It has many dimensions that need to be considered. If you follow the chat, you can also see there are strong opinions on some of these topics. I think all 3 presentations had a bit of a European perspective on this. So question perhaps from a World Bank perspective is also, okay, what now for a developing country that wants to export? Does all of this apply, or would some of the answers be a little bit different? But I want to give the audience chance to ask questions. If you have questions, please raise your hand.
In the meanwhile, Dolphin, to break the ice, I can say that yes, European, but for example, in my last part, this Desert Energy, DII, is looking at many countries which are out of Europe, starting from Morocco, Mauritania on the Atlantic Ocean up to Oman, which is in Asia, in the India, facing Indian Ocean. And from there, export can go worldwide, anywhere. Maybe just to remain to the title of this workshop, the integration between electricity and hydrogen sector is more important in places like Europe, where we have a very meshed electricity network, and we will produce hydrogen for local continental consumption. But in most emerging countries, many projects, most of the projects are the opposite, to build energy hubs with production, so not impacting the local grid, and then exporting this primary energy, which typically can be sun, wind, but could be also hydro somewhere, in another form, in another vector. For example, from Central Africa is too far away to go to arrive to Europe. You could do with hydrogen, as long as the cost of supply chain becomes, because this is the main problem. But so in all these emerging countries you are looking at as World Bank, maybe it is less important, the integration of electricity. And so I would split in two this issue, two different base cases and two different type of solutions.
Thank you for that important addition. I see no hands raised, but I see a question in the chat about the flexibility of electrolyzers. We're currently looking at the topic, and we hear different things and a little bit confusing things. First of all, the question of whether alkaline or PEM, whether the PEM is really more flexible than the alkaline. And the second aspect is, should you really operate electrolyzers in a flexible way? Because the lifespan of an electrolyzer is impacted if you vary the load a lot. So any views on these aspects?
I mean, on the models that we have analyzed, and this is one of the points that we were also in the chat about connected to the grid or not connected to the grid, the hydrogen production. On the models that we have right now, because I think this is going to be developed in the next 5 years, it's I mean, to use on a base model the electrolyzer, or on a flexible way of flexible model, it makes to get it older much faster, the flexibility way than the base model. So if you are thinking on a huge hydrogen production, 1 gigawatt or something like that, it needs to be on a base mode. Otherwise, it's not economical profitable for the investor. The small producers can be much more flexible. This is the models that we have been using. And it not depends so much on the technology. It depends on the use of the electrolyzer.
If I can add, yes, it depends on technology, because there are technology limitation, technology also options. It can be, for example, this maybe deserves what we are spearheading also as grid operators, to do more innovation and research, basic research on what is the chemistry or maybe balance of plant, which is constraining or can release the constraints to have more flexible operation. So maybe with small additions from engineering point of view or chemical, but maybe also engineering. And the main point you mentioned, the life can be reduced. Yes, there is no free lunch in this. It's always a cost of balancing the benefits you have, because you sell services. You would in the future also be called to give these services in an obliged way. I remember that the first renewable plants were free to connect without constraints. And then when they became the dominant part, I'm talking for my country, my continent, Europe, they were suggested to retrofitting. So they had to spend money or mandatorily to be connecting in a certain way, not to be free to disconnect in case of disturbances on the grid, etc. So might also be a good investment for the future. And anyway, we have the same case for electric vehicle charging. If you do smart charging, somebody doesn't want because the battery can be degraded. We conducted some studies that within certain limits, the battery can also gain longer life because you can have a type of charging, if it is controlled, which is good for the system, good for the owner, and good for the battery, a win-win-win solution. And this is what we should at least try to explore.
On the operation of the electrolyzer, I think one of you showed the duck curve and so on. So should at the current economics of electrolyzers, should we aim for maximum hours of operation, as some of you argued, or should we aim for operation at when the electricity is free? Is that model feasible at all? Or should we forget about that?
Of course, we don't know yet. If I start answering, we don't know yet about all the different possible payments for flexibility services. But so far, I haven't done any calculations myself over the years where we have been able to compensate for very few hours.
What I can add is that you can make a simple Excel calculation or more sophisticated, and there are around models with all the real cases application and make sensitivities, because also in the long life, 10, 20, 30, 40 years of the electrolyzer, you will have different conditions. Probably you can find the minimum the minimalizing condition. But if you remember the graphic also shown by Deloitte colleagues, it's more impacting the price of electricity than the number of hours after a certain threshold. If you go to below 1,000 or 2,000 hours, then it's much more impacting on the LCOH, the number of hours. Otherwise, we are in a more flat situation. So it's a calculation that you can do from almost a thumb rule with Excel to more sophisticated one, and has to be done case by case. This would be my answer.
I think, as you said, it's case by case. I mean, it depends on the off-taker. If you have a plant, that hydrogen production plant, and you have the off-taker next to the plant, and the off-taker can use the hydrogen in a flexible way, probably the mix of both things will work. Or if you are in a valley, you can substitute one production with another one. But if you are thinking on huge production for exporting or whatever, the price is going to go down as much hours you are producing.
No, of course, this is if you are connected to a grid. If you are off grid, then you have to go for the maximum hours, of course.
But as I always mention when we speak about economical part, it's also a question on whether there are additional benefits you could have from building a hydrogen system. It could be to serve as a backup solution or to increase the security of supply and so on. So of course, it's not only a question of the cost, the levelized cost for hydrogen. It's also a question on how much further services the system could provide.
Yes, for example, if you are on grid where you have a market, again, the case of Europe, because I know, sorry to be Eurocentric, but in that case, the system will expect from you that you use electricity with the low, zero, even negative prices. Some regulations accept that, because you make you are good for the system, because you are consuming surplus electricity which could not be consumed, should be curtailed. So in a sense, yes, if you are in that situation, I agree with it.
Very good. I still don't see any hands raised. This is your last chance as an audience to ask pertinent questions. Herman, please.
Dolf, thank you very much, colleagues. My name is Herman Jonker. I'm with the Western Cape government. It's a subnational government in South Africa. I've posted one or two questions. The second one, I feel a little bit intimidated by the technical knowledge in the room, and I always provide this caveat as someone who has an economics background. We struggle with electrons and molecules. But maybe just found it absolutely fascinating. We're in the middle of a funding application for a study to show some of our national regulatory bodies what green hydrogen projects could add in terms of load and generation power to our grid, a grid which is currently already under a lot of pressure and a little bit fragile. But right now we're promoting green hydrogen projects mainly from a private sector perspective. These are investors that have seen the possibility of low renewable energy costs in relatively close proximity to a potential export port, and some of the infrastructure elements already being in place, and some of the best renewable resources being not too far from where we have some decent but not perfect infrastructure. These projects are all going ahead, chasing financial close, as most big hydrogen projects across the world are. And they have no time, I guess, or patience to think about the energy system of the country or the region, but rather just to make their project work, which is perfectly fair, and that's where government has a job, right? But at this stage, the first 2 or 3 big projects, gigawatt scale projects, are likely to run way ahead of government being able to see them as integrated system components. And my question really is, how easy is it to still gain benefits to both the system and these individual projects if they weren't designed like that from the start? They're being designed right now, just each project on its own, some grid connected, some not. But that project must work, and the project developer needs to get financial close, build the thing, and prove it. And they couldn't care less about the system, whereas some system components, obviously, if they could be guaranteed upfront, would help them a lot, but they can't because we're not running fast enough. How easy is that sort of integration, benefit creation later on?
If I start, then, do you think about, for example, utilizing excess heat and oxygen and that type of integrations, or also for flexibility questions, which? Yeah,
the grid is our main concern at this stage. In other words, excess electricity when there's more sunshine and wind than the electrolyzer can cope with. And the other way around. But some of it is as basic as one portion of our grid having around 2,000 megawatt of load on it. And the next single proposed hydrogen project is 1,000 megawatts. So, 50% increase on electrons, or more or less 50% increase on load on a portion of the grid that is already struggling to just cope with what's there. So we're trying to tell our grid colleagues, please build, 1.5 times the size that you expect. And they say, where's the project going to be? When is it going to take off? Where is it going to produce the electrons, and when? And then maybe we'll start putting it in our 10-year planning cycle. So in 10 years, we'll be ready for you.
Well, Herman, there is a point which is not technical, so understandable by everybody, which we didn't touch very much. Until now, every project of hydrogen, green hydrogen around needs incentive. You can discuss its supply side, demand side, general financial, technical, on the capex, on the opex, on the off-taker, guarantees, etc. But they need incentive. Incentive means money, public money. And also investing in the grid is public money, because in, I would say, all countries, the tariff, the grid operator are paid through a public tariff. So this element, if you are, now you are the one who asks, but if you were the one to give money, public money, you need to give the public money, either incentive or grid expansion, to a project which is sound, which is which has benefits which are higher than costs. So this is also an issue to consider, not only the business case or the grid case. It has to be decided at a higher level, not grid operator, not electrolyzer businessman, but at a higher. It's a real policy issue.
And I was going to say that, of course, it's not that simple. You have to be very lucky if you can do changes afterwards when you already built the plant, I would say, since a lot is about location and land availability and so on. So that's my answer to you, Herman.
We have reached the end of our session. It's 10:30 here in Washington. I would like to thank our speakers, Cecilia, Alberto, Noe, and Antonio, for very insightful presentations. And thank you for answering the questions of the audience. I thank the audience for their active participation. My takeaway from this session is that this is an important topic. It has many dimensions, more needs to be done, and that can help to accelerate hydrogen deployment. So we will pay more attention there. So thank you very much. And I wish you all a nice day, and please join for our future webinars. Thank you.
Thank you.
Pleasure.
Thank you.
Thanks to you,
Bye.
Dolph, and to World Bank for raising this important issue.
Yes.
Thank you.
Cheers.
See you.